was a beautiful day, the sun beat down, I had the radio on, I was driving.
Okay, section 8.4 is on derivatives of logarithmic functions. Now, there's a lot of stuff to say here, and I think I've overdone it with these proofs, so I'm going to do the proofs very quickly. But anyway, we have four different derivatives here that are very important, and I will provide a proof of each one of them. Of course, I'm not going to make you memorize them or anything this year, but you might have to next year, and maybe it's helpful and useful, important even, to show you the proofs. But I am going to do them fast. So here's the first one. The derivative of the natural logarithm of x is equal to 1 over x. So let's prove this. Let's let y equal the natural logarithm of x. Okay, if we switch this into exponential form, remember the base here is e, so you'd have e to the y equals x. And the next thing we'll do is we'll do implicit differentiation. So the derivative of e to the y power, the derivative of e to anything is just e to the same thing, so it's e to the y. However, we have to do this implicitly, so we have to multiply by y prime. And on the right hand side, the derivative of x is 1. Now we want to isolate the y prime, so we get y prime equals 1 over e to the y. And if you look right back up here, we said that e to the y is equal to x. So in other words, y prime equals 1 over x. Done. Derivative number 2. The derivative of the natural logarithm of the absolute value of x is also equal to 1 over x. Okay, let's prove this. Well, first of all, let's be clear that x cannot equal 0, since the argument has to be greater than 0 in logarithms. B has to be greater than 0. Okay, so there's two cases we have to look at. One is if x is greater than 0, and the other one is if x is less than 0. Well, if x is greater than 0, then what we want to do is take the derivative of the natural logarithm of x, right? Because the absolute values don't do anything, we can just write it like that. And we just did that over here. We know what that equals. It equals 1 over x. If it's less than 0, then what we want to do is take the derivative of the natural logarithm of negative x, right? Because that's what absolute value signs do. If you have a negative amount, they make it negative negative or positive. Okay, so let's take a look at that. The natural logarithm of anything we just learned is 1 over that thing, so 1 over negative x. And then the chain rule tells us we have to move inside and take the derivative of negative x. Well, the derivative of negative x is negative 1. So we have negative 1 over negative x, which is the same as 1 over x. So in both cases, you have the same answer, which is 1 over x. Derivative number 3. The derivative of b to the x power is equal to b to the x power times the natural logarithm of b. Okay, they're getting more tricky, these proofs. Here's the next one. Remember, first of all, that e to the natural logarithm of b is just equal to b. This is one of our properties of logarithms, right? So, therefore, the derivative of b to the x is exactly the same as the derivative of e to the natural logarithm of b to the x. Does that make sense? All I've done here is replace this b right here with this amount right there, right? There it is right there. Just replaced it because we've already stated that these two things are equal to each other. Okay, so now we just have to take the derivative of this. Well, the first thing we would do is take a look at the outer function, which is e to the something. So it's just going to stay the same. It's still going to be e to the natural logarithm of b times x. And then we have to multiply that by the inner function, which is the natural logarithm. Maybe I'll even write this down. We have to multiply it by the derivative of the natural logarithm of bx. Okay, so this first bit obviously stays the same, times. Okay, the derivative of this is the natural logarithm of b. That's a constant amount right there, this natural logarithm of b. So if we're taking the derivative of the natural logarithm of bx, the answer is just the natural logarithm of b. Now look back up here, you see this highlighted bit? This e to the natural logarithm of b, we have that right here again, and that's equal to b. So what we actually have is b to the x times the natural logarithm of b. And that's exactly what it states here. Okay, the last one of our derivatives we're going to worry about. The derivative of the base b logarithm of x is equal to 1 over x times the natural logarithm of b. My goodness. So again, we're going to do something a little complicated that's not too intuitive. We're going to let y equal the base b logarithm of x. So if we change that into exponential form, you'd have b to the y equals x. And now let's use implicit differentiation again. So if we have b to the y, well, that just matches this over here, except instead of putting x, we're putting y. So we're going to have b to the y times the natural logarithm of b. But wait a minute, this is with y's, so we have to differentiate implicitly, so we have to multiply by y prime. And on the other side, we just get 1. Okay, solving for y prime is very easy. It's 1 over b to the y power times the natural logarithm of b. And then we see that b to the y is just the same as x. So in this statement right here where it says b to the y, we can just write x right there. And we end up with exactly the answer we're looking for. So there you go, our 4 derivatives along with proofs of each one of them. Okay, finally, let's take some derivatives. So the first one, y equals x times the natural logarithm of x. You know what you're going to have to use here? You're going to have to use the product rule. So for the product rule, y prime equals, the way I do it is I take the derivative of x, well that's just equal to 1, and then I multiply it by the second one, which is natural logarithm of the x, plus the first one, x, times the derivative of the second piece, the natural logarithm of the x. Well, we just learned up here that the natural logarithm of x is equal to 1 over x, right up here. Natural logarithm of x, the derivative of that is equal to 1 over x. So we're multiplying by 1 over x. Okay, so 1 times natural logarithm of x is just natural logarithm of the x, and here you have x times 1 over x. The x's cancel, you're just left with 1. And there's your answer. Okay, next one. This one you're going to have to use the chain rule. So the outer function here is the natural logarithm of something. So how do you take the derivative of the natural logarithm? Just did it over here, you do 1 over. So we have 1 over cosine x multiplied by the derivative of the inner function. Well, the inner function is cosine x. What's the derivative of cosine x? It's negative sine x. So what we end up with is negative sine x over cosine x. But wait a minute, that's actually a trigonometric ratio that we can simplify. What's sine over cos the same as? That's tan. So we end up with negative tan x. Okay, here's another chain rule. Our outer function is something to the 4th power. So we're going to use the power rule. The 4 comes down. Still have the same inner function, but now it's to the 3rd power, times the derivative of the inner function, which is natural logarithm of x, and that's 1 over x. So our final answer would be 4 times the natural logarithm of x cubed, all divided by x. Okay, the next one. Okay, you can do this one by using the chain rule with an outer function of natural logarithm, which means 1 over, or reciprocal, and then the inner function you'd have to use the quotient rule. It's really hard. You can do it, but it's a good practice actually to try it. But I'll show you an easier way. This is the nice thing about logarithms. Remember, one of the powers of logarithms is you can write them in different ways. We could expand this logarithm. Instead of writing this as a single logarithm, we could write it as 2 logarithms with the same base. So the natural logarithm, we could have natural logarithm of x, and then what would we do because of this bottom piece? We would subtract the natural logarithm of x plus 1 to the 1/2 power. And in fact, what we could also do is move that 1/2, we could scuttle that out front. So we end up with this. And this is going to be a lot easier to take the derivative of. So that's actually what I'm going to do. I'll change colors now to show we're actually taking the derivative. Y prime. Well, the first piece is very easy. This right here. Natural logarithm of x, that's just 1 over x. Minus. Okay, so this is just a constant, so we can write that 1/2. Then we use the chain rule. So first of all, we have the natural logarithm of something, which means 1 over that same thing. And then we're going to multiply that by the derivative of the inner function. Well, the derivative of that is just 1, so it's not going to make any difference at all. So we end up with y prime equals 1 over x minus everything on top of 1 And on the bottom we have a 2 and an x plus 1. Okay, next question. I'm going to write the derivative over here that we need to know because I don't want to keep flipping back and forth on the page. It's difficult. So here it is. The derivative of b to the x is equal to b to the x times the natural logarithm of b. Well, in this case, we have 2, which is our b there, and our x squared is actually the x. So we actually have a chain rule here again. The outer function is 2 to the something. So how do we take the derivative of that? We follow what we did here. We have y prime equals 2 to the x, well remember in this case it's x squared, times the natural logarithm of b, which is 2. And then you have to multiply that by the derivative of the inner function, which is x squared. So the derivative of that is 2x. So you could write this in different ways. Maybe what I'll do is I'll put this 2 and this natural logarithm of 2 together. So I have 2 times the natural logarithm of 2, and then what's left is still an x and a 2 to the x squared. I mean, you could do this in different order. That's not a multiplying sign, that's an x there. Okay, again, I've written the derivative we need over here just so we don't have to flip back and forth. So we have the base 10 logarithm, which is just a common logarithm, I don't know why I put the 10 there, of 3x plus 1 all to the 4th power. So again, chain rule here. So f prime of x equals, first of all, we're going to have to use this derivative for the outer function, which is the base 10 logarithm. So you'd end up with 1 over x. Well, x is this whole 3x plus 1 to the 4th times the natural logarithm of b. b is the base, and in this case the base is 10. I really wish I hadn't put that. I was kind of giving it away to you. And then we're going to multiply by the inner function, which is this, and we got to use the chain rule in this as well. So the 4 comes down, multiplied by times 3x plus 1, now it goes down to the 3rd power, and then we take the inner function of that, and we take the derivative of that, which is 3. So if we multiply that all together, on the top we have 4 and 3, which is 12, times 3x plus 1 cubed, all over 3x plus 1 to the 4th. Oh, wait a minute, that's the same thing. And then a natural logarithm of 10. Look at, we got 3x plus 1 to the 3rd, 3x plus 1 to the 4th. So these all go away, and all 3 of those go away. We're just left with 1. So our final answer is 12 over 3x plus 1 multiplied by the natural logarithm of 10. Man, I wish that was the end of the video. It'd be a nice length video. Instead, I still need to sketch a graph. No. Okay, here we go. Domain. Well, remember the argument, the x squared minus 1, has to be greater than 0. So the way I solve quadratics is I temporarily make it equal to 0. Solve that. So you'd have x plus 1, x minus 1, if I factor, is equal to 0. So x is equal to plus or minus 1. So on a wiggle graph, if I put negative 1 and 1, we'll now try some points back in the original here. If I put 0 in there, I get 0. Take away 1 is negative 1. Is that greater than 0? No. If I put 2 in there, I get 2 squared minus 1 is 3, and 3 is greater than 0. So this works. This doesn't work. This is also going to work, right? If I put negative 2 in there, it also squares to get 4. Minus 1 is 3. It's also greater than 0. So these are the areas that work. The domain is from negative infinity up to negative 1, not inclusive, remember it's just greater than, as well as from 1 up to infinity, not inclusive. Okay, the intercepts. Let's look for the y-intercept first. That's easier. We just put 0 into the x. So you get the natural logarithm of 0 squared minus 1, the natural logarithm of negative 1. Hey, wait a minute. You can't do that. So this is none. No y-intercept. For x-intercept, we have to see when does this equal 0. So I'm going to say 0 equals the natural logarithm of x squared minus 1. To solve that, why don't we put an exponential form? Remember our base here is e. So we get e to the 0 equals x squared minus 1. E to the 0 is just equal to 1. So 1 equals x squared minus 1. Move the 1 over, you get 2 equals x squared. Take the square root, you get plus or minus 2. So our x-intercepts are root 2. Did I say plus or minus 2? Should have been plus or minus root 2, right? So root 2, 0, and negative root 2, 0 would be our intercepts. Symmetry. Well, the only x we have is right here. And if you put a negative x in there, you're going to square it. It's going to become positive again. It's going to be exactly the same. So that means the symmetry is even. symmetry across the y-axis, right? Okay, asymptotes. Let's take a look at the limit of this function as x approaches infinity. So if you put infinity in here, you're going to get a massive number. Take away 1, you still have a massive number. So you'd be asking yourself, e, that's the base, e to the what equals basically infinity? Well, e to the infinity. So this equals infinity. And even if this was negative infinity, it would still be the same result, because when you square negative infinity, you get positive infinity. Take away 1, still positive infinity. E to the what equals positive infinity? Infinity. So this limit approaches infinity, which means there's no horizontal. It's useful to know that, though. We'll know that it goes up towards infinity as we head out in the x direction very big, or an x direction very small. So it's still useful to know. Okay, for the vertical asymptotes, we should look at these two spots, the -1 and the 1, and specifically we should look from the right hand side here and the left hand side there. So let's start with this one, maybe a little bit easier. So the limit of the natural logarithm of x squared minus 1 as x approaches 1 from the right hand side. So if we put a number just a tiny bit bigger than 1 and then square it, it's still going to be just a tiny bit bigger than 1. And then we subtract 1, it's going to be just a tiny bit bigger than 0. It's just going to be a tiny positive. So we're interested in what's the natural logarithm of a tiny positive equal to? Well, remember, the base is e here. So what we're looking for is that e to the something equals a tiny positive. What goes there to make it a tiny positive? Well, it's not a positive number, because e squared, that's like 2.7 squared. E to the 1, that's 2.7. Even 0 doesn't work well. E to the 0 is just 1. That's not that small. How do you make it smaller? Make this exponent here something negative, right? The more negative you make it, the smaller it'll be. If this is -1, you get 1 over 2.7. If it's -10, you get 1 over 2.7 to the 10th power. So how do you make it as small as possible? Make this exponent as negative as possible. In other words, we want this answer to be negative infinity. If you were to do this whole thing again, but do a little bit smaller from -1, the left-hand side of -1, you'll see you're going to get exactly the same amount. How come? Because when you square that amount, you're going to end up with the exact same situation we had here. So in both cases, it tends towards negative infinity, and this means we have vertical asymptotes at both those spots. So I'll say x equals plus and minus 1 are vertical asymptotes. Okay, at last we can take the derivative here. So the derivative of this is not too bad. Y prime equals outer function's natural logarithm, which means 1 over x squared minus 1, multiplied by the derivative of the inner function, which is 2x. So we have 2x over x squared minus 1, but maybe how I'll write that is x minus 1, x plus 1. So the points we have to look at are anything that would make the denominator equal 0, which is -1 and 1, as well as anything that would make the numerator equal 0, which is 0. But remember, the domain did not include between -1 and 1, so we don't even have to look at these at all. All we have to look at is these two regions here. Where do we look? Back here. So we're going to try some stuff in there. Let's try 2. If we put 2 in there, I get 2 times 2, which is a positive. I get 2 minus 1, which is a positive, and I get 2 plus 1, which is a positive. It's all positive. So this part here is increasing. Now let's try putting -2. If I put -2 in there, I get 2 times -2, which is a negative. I get -2 take away 1, which is a negative, and -2 plus 1, which is a negative. 3 negatives make a negative. So this part is decreasing. Maximum or minimum? Well, even though it has negative here and positive here, you might be tempted to say there's a minimum. You have this gap here of nothing, so no, there's no maximum or minimum. Look at this, the biggest space, and all I have to write is none. Concavity, we got to take the second derivative. Sadly, we're looking at a quotient rule here, so we're looking at this box part, but let's think of the bottom as x squared minus 1, it'll be easier. So we take the derivative of the top, which is 2, and we multiply it by the bottom, which is x squared minus 1. We subtract the top, which is 2x, and the derivative of the bottom, which is 2x. And that's all over the bottom, x squared minus 1 squared. So if I expand here, I get 2x squared minus 2, and then I have minus 4x squared, all over x squared minus 1 squared. So 2x squared minus 4x squared is negative 2x squared minus 2 all over x squared minus 1 squared. I can factor out a negative 2. I get x squared plus 1 all over x squared minus 1 squared. And we can put this on our wiggle graph. So what would make the bottom equal 0? If it was 1 or negative 1. What would make the top equal 0? Well, this inner part here would have to equal 0. How do you make x squared plus 1 equal 0? You don't, because you get x squared equals negative 1, and that's impossible. So again, these are only points, and again, we don't have to consider this because this is not part of the domain. So again, we just have to try on each side of here. And where do we try it this time? Right here. So if we put 2 again, you get 2 squared, which is 4, plus 1 is 5, so that's a positive, times this negative. So you got a negative times a positive. On the bottom, you'd have 2 squared, which is 4, minus 1 is 3. It's all squared anyway, so it's going to be positive. So you have negative, positive, positive, which means this is going to be negative, and that means it's concave down. Over here, if we put negative 2 in there, we'd have the negative 2 here. Negative 2 squared is positive 4, plus 1 is still positive. And on the bottom, it's all squared, so it's going to be positive. Hey, this is also concave down. Now we're looking for points of inflection. Again, we have this big gap separating this. In fact, it's all concave down, so again, this is none. Okay, time to graph. This is crazy, isn't it? Here's positive 1, here's negative 1, and remember we had asymptotes at both of those. Here's 2, here's 2. But remember our x-intercepts were at root 2 and negative root 2, which is at about 1.4. So we got a point around there and a point around there. Domain did not include anything in here, so this should all be empty in there. Remember the asymptotes, it tended towards negative infinity at both cases. So you'd think it would go probably something like this. And we said as we go out, remember that it tended towards positive infinity. So I'm suspecting it might go something like this. I don't know exactly what it would look like, but something like that. And let's just check that. In terms of increasing, decreasing, it's supposed to be decreasing here, yes, and increasing here, yes, it is increasing. And in terms of concavity, it should be concave down here and concave down there. Yeah, this is pretty awkward in the middle here. I did a pretty poor job, but you get the sense this is what it looks like, something like that. In fact, there you go, and that looks pretty darn close to what we had drawn right here. So good job. It's just sad that it took that long.
Yeah, running down a dream.